Alright, uh, good afternoon, everyone. I'll be presenting the lesson on differential amplifiers. Yeah. So for the basics of the differential amplifier or diff amp, basically the differential amplifier is mostly known for being built with having two separate input voltages and two separate output voltages. But the interesting thing about the diff amp is that it can also function while only using one input voltage, but still have separate output voltages coming out of two sides. As you can see in the diagram here, it also looks like an operational amplifier. In fact, the operational amplifier is actually one type of a diff amp, specifically when each of the two inputs have specific polarities. Anyway, from the feature of having two inputs but optionally one, there are three configurations that go out of a differential amplifier. The first is the single-ended differential amplifier. This is the one I just mentioned, where it can function with only having one input voltage but still having two output voltage values. This basically works like the differential amplifier takes that single input voltage to be the voltage that runs through the entire circuit, as if it is the sole input voltage. So basically, this means that you can use that input voltage value to solve for the output voltage of either one of the transistors. And the property of that is the output voltage of one transistor would be equal to the output voltage of the second transistor. The reason for this is because there's only one emitter current that runs through the entire circuit, and it is divided into two collector currents that go across the left and right side of the circuit. So basically IC1 and IC2. And since IC1 and IC2 are exactly equal, since they are the equal halves of the emitter current, they run through the same value of RC. RC1 and RC2 are equal, so are IC1, IC2. And then they run across the same transistors, which have the same values as well, and they share an RE. So naturally, their output voltage at the end of the process would be equal, but they're still separate processes, which is why they have two output voltages, but they are exactly the same. So for the second configuration, you have the double-ended differential amplifier. For the double-ended differential amplifier, this is when you use the two input voltages. Specifically, these input voltages have opposing polarities, the inputs, and the output voltage coming from the difference comes from the difference of the two input voltages. What this means is that if you have the voltage gain formula, you have V over VI. The formula becomes VO over VI1 minus VI2, the difference between the two input voltages, since they are opposing polarities. The solutions that go into the double-ended configuration are basically the same as a single-ended, apart from what I just mentioned of the input voltage being the difference of each of the two input voltages. You will see what I mean later. For the last configuration, the common mode configuration, it uses two inputs from the same voltage source. What this means is that you have a VI1 and a VI2, but they both come from the same source. Like if nakay battery and duwa siya ka wire, duwa ka connecting ports, both sides of the amplifier are connected, but still they come from the same battery. We'll go back to the logic of the double-ended configuration, wherein the input voltage is the difference between the two inputs. If you apply that logic in the common mode configuration, then you would basically be subtracting input voltage from itself. And so the input voltage would virtually be zero. But it is commonly accepted for practicality reasons that it is not exactly zero, and there is still a bit of input voltage going into the circuit in a common mode configuration. And there would be an equivalent small amount of common mode voltage gain. Here you see the different configurations of a differential amplifier. On the left, you have a double-ended differential amplifier. As you can see, there are two sources, VI1 and VI2. If you want to make this a single-ended differential amplifier, you can take away VI2, so you only have one source. It's just simple as that, since the process is the same, like I mentioned before. And for the right diagram for figure 10.18, you have a common mode differential amplifier. As you can see, like I said, there's only one source, but it works as two input voltages on both sides. Now here are some applications of the differential amplifier. you'll find that differential amplifiers are mostly related to noise. Noise is basically the interference that comes along with any electrical signal that is transmitted. Differential amplifiers are configured so that they are at least able to minimize noise and in best situations, in ideal situations, able to block it out. It's also used for amplitude modulation. We all know that this is when the amplitude of a certain signal changes and varies depending on the strength of the signal, also used in radios. Negative feedback circuits is when um, the output voltage, some of the output voltage goes back into the input voltage. And considering the relationship between input voltages and output voltages in differential amplifiers, this comes as no surprise. And lastly, for the high pass filter circuit, differential amplifiers basically help in the ability to uh, allow signals that are greater than a cutoff frequency to pass while attenuating signals that are less than a certain cutoff frequency. So for the theoretical calculations of a differential amplifier, similar to the BJT and FET solutions that we have discussed before, there is a DC analysis and AC analysis. For the DC analysis, the same process is followed for the DC analysis, regardless of whatever configuration you're talking about. Single-ended, double-ended, and common mode all have the same process for the DC analysis. In this particular picture, it's a double-ended, but both of them are zero anyway, since this is just an example. For the KVL equation of DC analysis, you have VE minus IERE minus the negative of VE, since lower VE is negative because of the zero. And then you simplify the IE equation to be VEE minus 0.7. 0.7 is VE, but it's always set to be 0.7, so it's better to just substitute it to 0.7. IE is equal to VEE minus 0.7 of RE. And IE being the emitter current is divided into two collector currents, as you can see here. Both one goes into the left side and one goes into the right side. So each collector current being the equal half of the emitter current is IE over 2 is equal to the first collector current, which is also equal to the second collector current. And lastly, for the VC1 and VC2, they are again both equal, and so they share the same formula, VCC minus ICRC, which goes along the sides here. For the example of a single-ended DC analysis, we look to example 10.1, calculate the DC voltages and currents in the circuit of figure 10.11. This is actually a double-ended differential amplifier. It has a VA1 and VA2, but they are not specified yet, since the input voltages don't really come into play in a DC analysis problem. So the given are VE 9 volts, VE is 0.7 volts, that is fixed. RE is 3.3 kilo ohms, and RC1 and RC2 are both 3.1 kilo ohms, and VCC is 9 volts. Now for the DC analysis, first you have to solve for the emitter current, which is VEE minus 0.7 over RE. So 9 volts minus 0.7 volts over 3.3 kilo ohms, you have an emitter current of 2.515 or 2.52 milliamps. And the collector currents are exactly the half of the IE. And so you just divide IE by 2 to get IC, you have 1.26 milliamperes. Lastly, for the voltage VC, you simply follow the formula VCC minus ICRC. VCC is 9 volts minus IC of 1.26 milliamps times RC, which is 3.9 kilo ohms. You have VC is equal to 4.09 volts. Now for the AC analysis, it's when it gets sort of specific. On the left diagram here, you have the same circuit that I showed before of a double-ended example circuit, no values really. On the right side, this is basically the AC equivalent illustration of the same circuit for AC analysis. Both of these are the same thing but are redrawn. Everything in the blue box here you see is basically the inner workings, inner parts of each transistor. Like this left box here is for the Q1 and right box is for the Q2. As you can see, it also has a current source. Also has IB1, RA1 beta, another IB1 and IB2 beta 2, IB2, RA2, and B2. For the single-ended AC analysis, here's an example of an AC equivalent of a single-ended differential amplifier circuit. As you can see, it only has one source, CDI1. So the formulas that go into a single-ended AC analysis, first, the assumptions that you have to make are that the IB1 and IB2, IB1 on the left side and IB2 on the right side are both equal and so can be called IB. RI1 and RI2 are also equal. Ri is given the formula beta times Re, where beta for beta 1 and beta 2 are both equal. Finally, Re is equal to 26 millivolts over IC. The KVL equation for a single-ended AC analysis is VI minus IBRI minus IBRI is equal to 0. Substitute the Ri for VRE, and then simplify to be 2IB beta RE. Isolate the VI1 and divide IB by 2 beta RE. So you have the isolated formula of IB is equal to VI1 over 2 beta RE. IC is also given the formula beta times IB, and since we've already solved for IB, we substitute that formula and we cancel out the 2 betas and you have IC is equal to VI1 over 2RE, or VI is equal to IC times 2RE. The set formula for VO is given to be ICRC, and so to get the voltage gain of V over VI, you simply substitute the formulas of each voltage. You have ICRC over IC2RE, and cancel out the two ICs. You have the single-ended voltage gain is equal to RC over 2RE. For an example of a single-ended AC analysis, calculate the single-ended output voltage VO1 for the circuit 10.17. As you can see, this is a single-ended single-ended differential circuit. Once again, we assume that all the betas are equal, all the RIs are equal, RCs are equal, and finally RE is 43K, VCC is 9 volts, VE 9 volts, and the input voltage is 2 millivolts. So of course, we first have to do DC analysis of the circuit. So to solve for IE, once again, we do the formula for IE, which gives us 0.193 milliamps, and divide that by 2 to get 96.5 microamps for your IC. Now, to do the AC analysis of the circuit, you then use your calculated IC to get RE, divide that by 26 millivolts, and then you have RE is equal to 269.43. After you get RE, you can jump straight into the voltage gain of the circuit. As you can see, AV is equal to RC over 2RE, where RC is 47K times 269.43. So we have a voltage gain of 87.22. Now, to get the output voltage VO1, you have to multiply the average voltage gain by the input voltage, which was given to be 2 millivolts. So 87.22 times 2 millivolts is an output voltage of 0.17 volts. For the AC analysis of a double-ended differential amplifier, we have the AC equivalent of a double-ended differential amplifier circuit. As you can see, it has 2 input voltages. The solutions that go into a double-ended AC analysis, everything before solving for RE is basically the same as single-ended. All of this happens in the double-ended AC analysis as well, apart from solving for average voltage gain. From the KVL equation all the way down to the equation for output voltage is the same for double-ended AC analysis. So once you get your IC, you have RE, 26 millivolts RC, and here you find the first deviation from single-ended. This is called the differential voltage gain. And to get the differential voltage gain, you need to divide the output voltage over the difference between the two input voltages. VD is equal to VI1 over minus VI2. So differential voltage gain is equal to output voltage over the difference of the two input voltages. Output voltage is once again equal to ICRC, and the difference of the two input voltages is equal to ICRC. So you substitute those two equations into the differential voltage gain formula, cancel out IC, and you have differential voltage gain is equal to RC over RE. For an example of a double-ended differential circuit solution, we'll once again look at figure 10.17. This is the same problem as before, except now it's a double-ended circuit. As you can see, I added a second input voltage of 1 millivolts. All of the given are the same. In fact, I just copied that and added the input voltage of 1 millivolts at the end. For DC analysis is of course the same, since like I said, the process doesn't change regardless of what configuration you're using, since it doesn't use the sources yet. So same, IE is 0.193 milliamps and an IC of 96.5 microamps. So for RE, the RE is also the same at 269.43, and the differential voltage gain is where things actually change. RC is 47 kilo ohms over the RE of 269.43. As you can see, the differential voltage gain is actually twice the voltage gain of the single-ended configuration of the same circuit where it was 87.22. This is because in the single-ended voltage gain formula, there was actually a 2 in the denominator where it's beside RE. This one doesn't have that, and so the differential voltage gain is effectively doubled. To get the output voltage, double-ended output voltage, once again, have to use the differential gain formula. So output voltage is equal to differential voltage gain times the difference of the two inputs. So you have 174.44 times 1 millivolt. And the output voltage, double-ended output voltage, is now equal to 0.174 volts or 174 millivolts. I should mention that this is equal to the answer of the single-ended problem, but only because while the differential voltage gain is doubled, I also picked a second input voltage that coincidentally halved the input voltage, and so it's the same. But if I chose a different second input voltage, then it would effectively be higher. Say, for example, I chose a VI2 of 0.5 millivolts, then it would be 174.44 times 1.5 millivolts, then the VO would be 0.26 volts, which is, again, still higher. The last configuration of AC analysis, we have the common mode configuration. As you can see, the AC equivalent of a common mode configuration, there's once again only one input voltage source, but it's going into two ports of the input voltage. And the solutions for a AC analysis of a common mode differential amplifier. It's basically we start with the Kvl equation of VI minus IBRI minus 2 beta IBRE minus 2 IBRE is equal to 0. Simplify that, you isolate the VI and you bring out the IB since all of those terms have an IB, where you have RI plus 2 beta RE plus 2 RE. Then from those, you bring out the RE, you have 2 beta plus 2, until finally you have the equation of VI is equal to IB, brackets, RI plus 2 RE, parentheses, beta plus 1. I have the formula of output voltage is equal to beta IBRC. This is actually the same formula used before, which is output voltage is equal to ICRC. I just changed it to beta IBRC here since there might be confusion as to whether the IC being used was the DC IC or the AC equivalent IC. So just change it to the AC formula of the IC. Finally, you have the AC voltage gain or the common mode voltage gain is again equal to output over input. So you just substitute the two formulas that we derived. You have AC is equal to beta IBRC over IB times RI plus 2RE beta plus 1. Cancel out the two IBs and you have common mode voltage gain is beta RC over RI plus 2RE, all multiplied by beta plus 1. For an example of the common mode voltage gain, we once again use figure 10.17. This time it is a common mode configuration circuit. As you can see, one source is being used on two input voltages. And yeah, same given basically, but these are the only given I listed since they are the only ones that are useful for solving for the common mode voltage gain. We just use the formula we previously derived, beta RC over RI plus 2RE, all multiplied by beta plus 1. Substitute the given of beta 75, RC 47 kilo ohms, RI 20 kilo ohms, plus 2 times RE 43 kilo ohms, all multiplied by beta 75 plus 1. So I have an IC of 0.538. Notice how it is very much smaller than both the single-ended and the double-ended configurations. This is because they are supposed to have a ratio where the bigger the ratio is of the double-ended voltage gain over the AC voltage gain, the better the amplifier actually works. For the last part, the constant current source, which was just previously mentioned in the previous report. Basically, as I said, the differential amplifier, one way to gauge how good it is as an amplifier is by getting its common mode rejection. The common mode rejection is basically the ratio between the differential or double-ended voltage gain of a circuit versus the AC or common mode voltage gain of a circuit. For these particular examples, rather, double-ended voltage gain was 174.44 versus common mode voltage gain of 0.538. Basically, the larger the ratio is, the better that differential amplifier works as an amplifier. And so you want to reduce your AC as much as you can. One way to do that is to increase the impedance of resistor RE. And one way to increase the impedance of resistor RE is by using a constant current source. So by using a constant current source, you're able to maximize your RE's impedance, ideally to be as close to infinity as you can, which would minimize your common mode voltage gain, maximizing your common mode rejection ratio. And yeah, more na to, sir.